Okay, so this video is going to show you how to use Simulink. So I'll place files here on the main Canvas page. So here's at the main page at the bottom, homework files. This file here, simplegen.slx, is essentially the file that you'll need for this first homework where we're using it. So what I do is I download that file somewhere onto my computer. In this case, I'm actually working on Mosaic, so you can see what it would look like there. To open that file, what I do is I just open MATLAB on Mosaic. And again, you could do this on your own computer. And then I go to the folder in which that particular file is located. And then I just type its name, simple_gen. What that's going to do is it's going to open up Simulink. It will take several minutes to open the first time. And I emphasize several minutes. Don't be surprised if it's 4 or 5 minutes for it to open up the first time. But what that'll do is it takes up a couple of different windows. So you'll see this window here. This has got the model file, and you'll also see several what we call oscilloscopes, all right, which I'm going to talk through here in a second. The oscilloscopes are where we actually interact with the output of the simulation. So this is your basic model. Basically, there's it's a little tricky to follow all the lines here, but basically what's going on schematically is I have a synchronous machine rated for 450 MVA at a 24 kVA line-to-line output. It's 4 poles, so 1800 RPMs. That thing is connected up to, over here, an infinite 3-phase bus. So if I follow here, these are phase A, phase B, and phase C outputs. And if I highlight this line, you can see phase A of the generator goes to phase A of the grid. Phase B of the generator goes to phase B of the grid. And phase C of the generator goes to phase C of the grid. Okay, so it's pretty straightforward. Then there's 2 inputs. One is the mechanical power input, PM, and the other is E. Basically, that's the EAF that we put in. Now, for you over here, the 2 things that you'll play with are the mechanical power input and EAF, the excitation voltage. Now, a couple of things that I can do when I run the simulation, I can change my inputs, run the simulation a particular way, and then I can look at the outputs. So basically, to look at the outputs, there's this oscilloscope over here, which has 5 inputs. And in order, you can see what they are. It's the power angle delta, the speed in RPM, the electrical power, that's the 3rd one. The power factor angle is the 4th one. And then the difference between the mechanical power and the electrical power is the last one. Okay. Then there's a bunch of stuff over here that does some computations for us. If you really want to know this M here, this is an output. It's all the measurements from the synchronous machine. Okay. So basically all this is a synchronous machine hooked up to an infinite bus. Okay. All right. So if I want to run this, what I do is I just go up to this little play button, hit that. You can see here it's going to run for 5 seconds. All right. You shouldn't need to change that at all. You shouldn't need to change any of the parameters about how the simulation runs. All right, once it's done, which I heard that little ding in the background, that means it's done. I can now click on the scope and I see all of my outputs. And then what I can do is I can kind of scale everything to fit the screen. So what I'm going to do is I'm going to hit this guy and it's going to fit all of those to the window like that. And in this particular case, what I see if I just go through this is it looks like the power angle is, other than some little transient blip that happens here, basically is at 0. It looks like the speed is at about 1800 RPMs. The electrical power is at 0. The power factor angle looks like it's about -90. And the difference between mechanical and electrical power is 0, which in steady state, it always should be. All right. Now, the fact that the power factor angle is -90 means there better be some current in this simulation. So if I go to the current oscilloscope, there definitely is some, and I can apparently this guy already sort of fits to the window. Okay. So what I can see here is there's some sort of a startup transient as this thing gets started, and then it gets into steady state. Okay. So a couple of things here. If I looked at this current better be 90 degrees out of phase with the voltage because it's telling me that my machine, if I looked at the scope here, the fact that this is at power factor angles at -90 tells me that this thing, and so the power factor is at -90, the electrical power is at 0, tells me this guy is taking in purely reactive current. So he's just sucking in Q and putting in no P. So if I look, that means that the way I gave you this as default means that my electrical power in must be 0. So here's what's going on. So basically what this says here is that, step at 0.5 seconds, I change my mechanical power from 0 to 0. So that basically does nothing. All right, you guys are going to play with that throughout this. So in other words, this thing is providing 0 mechanical power. So it makes sense that I was getting 0 electrical power. Now I was also getting some reactive power, and that would just happen on the basis of the fact that in this case, I have EAF equal to 0. You should be able to sit down and think about the circuit model. If EAF is equal to 0, that would give you basically just an inductor connected to the grid. All right. Let's say we wanted to change something. So the way that you guys would change stuff is, and I guess one other thing I should say, if I double click, so it's a double left click on the machine, that opens up this thing that says block parameters for this guy. The things that you will play with a little bit are here on the parameters page. So I have defaulted the values to what they need to be. You don't need to touch these except when explicitly told to do so. Okay. Which I'll show you here in a second. So I'll just click OK to close that out. Now, like in the beginning of the problem, I say, you need to set EAF. So let's just say for sake of argument that you decided to set EAF to, I don't know, 30,000. Okay. And I'll click OK. I'll see that change here. I'm going to keep the mechanical power at 0. I'm going to run this thing. So if I kept the mechanical power at 0 when I run this, the electrical power should still be 0. So let's take a look at what happened. All right. So let me reset this. Okay. So here's what happens. I can clearly see sort of the transient effects kind of taking place here. So looking at this, the electrical power we said should be 0. And this says that this guy actually reaches pretty high, up to almost 2.5 times 10 to the 8. But by the time I get to steady state, it's at 0. So there is a transient, and Newton's law would tell us that during the transient there would be some electrical power, right? And I can see the difference between electrical and mechanical. There's some at the beginning and then eventually goes out to 0. Similarly, I see with the power angle, it has some initial change, but eventually gets itself to 0, as it should if there's no electrical power. Speed changes initially, but eventually gets itself to 0, or sorry, to 1800, since there's no power. Okay. All right, so we can kind of make sense of these different things. Now, a couple of things that you can also change. Let's say I did want to apply a change in mechanical power. So I can set let's start it initially at 0. And let me set this to, let's say, 100 megawatts. And I'll click OK. And I can run it. That tells me that in steady state, I should see the electrical power get itself to 100 megawatts as well. All right. Now, so here's the result, and I can see some stuff going off screen. And one thing I didn't talk about on that last one, if I click this button here, scale X and Y axis limits, it fits everything properly to the screen. Okay. And so I can make some sense about everything going on here in terms of the final values of the power angle. The speed eventually gets to 1800 RPMs like it should. If I went through my calculations here, I could figure out why the power factor angle is, I don't know, it looks like he's about 30-ish degrees. And I can see that right here, this guy gets 1 times 10 to the 8th. Once he gets to steady state on the electrical power, that also makes sense. And then in steady state, P mechanical minus P electrical also gets to 0. Now, if I wanted to read the values off of these things, what I can do is use this thing here, the cursor. So let's say what I want to do is I want to read the value of the power angle delta during steady state. So right now, this is how I can control which one I look at. So it says the power angle delta in degrees. That's the active one. So what I can do is I can use these cursors here. So to use the cursors, I push this button. That turned them off. I push it again. I'll turn them back on. All right, and then I'm going to move this here. Notice as I move this, I'm just left clicking and holding it to move it. what that's doing is it's moving the values over here. So in this box, it tells me for cursor number 1, which is sitting right now at time t equals 3.061. So if I look here, this is 3.061. And then number 2 is apparently sitting at 3.75. The value of the current variable at that point are these two numbers, right? So right now, what this is saying, the power angle delta at cursor number 1 is 15.68 degrees, and at cursor number 2 is 15.63 degrees. So if I move this along, probably it's the case that the power angle is kind of bouncing around about 15.6 degrees. Okay. Now let's say you wanted to read the steady state values. What I could do is the power angle I've got looks like it's about 15.63 in steady state here at number 1. And let's say I wanted to look at the speed. So I can click on this little drop down, go to the speed. Now notice that the little dot moved from the top graph to the second graph. And I can see that at point number 1, I'm at 1800 RPM like I would expect. The electrical power, if I go to that one, electrical power point 1 looks like it's 99.98 megawatts, which is about what I would expect. There's probably a little bit of power being lost because this machine has some resistance to it. If I want to see the power factor angle, right, I can see that the power factor angle is about 30 degrees, and the difference between the electrical power and the mechanical power is pretty small. And the reason, again, that there's a difference probably is because there's some losses in this machine. Okay. All right, so it's pretty straightforward to use. For the current, like let's say you wanted to read the peak value of the current. So the current looks a little bit funny here. Let me rescale it. There we go. Now notice there's sort of a transient period going on here, and the current's not settled around 0 because there's some L over R time constant in the machine as it gets started, but eventually the current gets settled around 0. What I can do, I can read values off of that just like I did previously with the cursor, but I might want to zoom in. So notice what I did was I clicked on this little magnifying glass. So I centered it up again. Then I click on the magnifying glass, and basically I'm holding down my left mouse button to select a little area, and then I can see this. It looks to me like the current's peaking out at about 4,000 amps. So if I wanted to get the RMS value, 4,000 divided by the square root of 2 would probably be close enough. Okay. So it's pretty straightforward to use. I do tell you at some point to change some parameters in here, right? So if I double click on the synchronous machine, go to the parameters, so one of the things I tell you to change the initial conditions. So it defaults to the initial value of delta, that's theta in this case, to be 15. Let's say I change that to 0. All right, and then it's ready to run. That will change some behaviors of this thing, as it should. I get the ding that it's finished. I open up the scope. Things have moved around a little bit, so I go ahead and recenter everything. And what I'll notice is everything I have should be able to make sense again. The currents and everything will be a little bit different. In fact, my current probably has much less of a transient now if I go and take a look at that one. All right, or at least a different transient, I guess. All right, so I've got a different transient of sorts, and everything kind of settles out properly. Okay. So again, pretty straightforward to use this guy. All I'm really asking you to do is not to build anything with it, but just to use it and interact with it. So hopefully that helps.